Hey guys, welcome to Taking Action Chapter 1. Thank you so much for joining me for my very first digital PD. This course introduces us to the 8 effective mathematics teaching practices. So let's get started. This digital PD series is based on the book Taking Action, which explores 8 effective mathematics teaching practices. The 8 effective practices are based on 25 years of research and are backed by NCTM. These practices challenge students to become thinkers and doers of mathematics. They support teachers in building students' conceptual understanding along with their procedural fluency. And research has shown that these practices improve student learning of mathematics. So let's check out these 8 practices. The 8 effective mathematics teaching practices are: establish mathematics goals to focus learning, implement tasks that promote reasoning and problem solving, build procedural fluency from conceptual understanding, use and connect mathematical representations, facilitate meaningful mathematical discourse, pose purposeful questions, support productive struggle in learning mathematics, and elicit and use evidence of student thinking. Our purpose in this course is just to become familiar with these practices. Each of these practices will be explored in depth later in their corresponding digital course. So let's take a look at the first practice, and that's to establish mathematics goals to focus learning. Goals indicate what students are to learn and understand as a result of instruction. Goals should identify what students are to know and be able to do. They should be understandable for both teachers and students. And we also have to consider how the learning goals relate to and build student understanding toward the rigor of our standards. Everything we do throughout instruction should be gauged against the goals. And we use goals to monitor student progress. But the type of goal also determines the type and the depth of the learning that our students experience. So let's take a look at a couple of goals. The 2 goals we're going to look at align to the algebra standard FBF 2.3. This standard says that students will identify the effect on a graph of replacing f of x by f of x plus k, k f of x, f of kx, and f of x plus k for specific values of k, both positive and negative, and find the value of k given the graphs. Goal number 1 states, students will create graphs that illustrate the different effects created by replacing a given function f of x with each of these for specific values of k. Students will explain the effects created. On the other hand, Goal 2 says students will be able to transform a given function. Both of these goals fall under this standard. However, the learning that takes place under the first goal could be very different than the learning that takes place under the second goal. Goal 1 is very specific about what students are to know and be able to do. It addresses the conceptual component of transforming functions by asking students to create graphs that illustrate the different ways replacing a given function, f of x, with each of these affect the graph. And it asks students to explain those effects. That builds an understanding of the relationship between the changes in the function equation to the changes they're seeing in the graph. and it supports developing their procedural fluency when working with transformation of functions. Students experience a deeper level of learning under Goal 1, and Goal 1 addresses the rigor of the standard. Goal 2, on the other hand, is a performance goal. Its focus is on the procedural. And it's not clear under the second goal if students will have a conceptual understanding of transformations. When writing goals, we need to make sure we're addressing the rigor of the standard, but also the conceptual and the procedural components of mathematics learning. Let's check out our next practice. And that's to implement tasks that promote reasoning and problem solving. These types of tasks are necessary in developing students' conceptual understanding. These are high-level tasks that require students to think through and make sense of a situation. These types of tasks should be open-ended and allow students to use their own mathematical understandings and their own strategies to figure it out. And learning is greatest in classrooms where the tasks consistently encourage this high-level thinking. We also have to keep in mind our students' prior knowledge and their current abilities when selecting these tasks. The tasks we select must be doable for our students, but still challenge them to reason and to think. So let's look at a couple of tasks. Task A says, you're trying to decide which of two smartphone plans would be better. Plan A charges a basic fee of $30 per month and 10 cents per text message. Plan B charges a basic fee of $50 per month and 5 cents per text message. How many text messages would you need to send per month for Plan B to be the better option? Task B says to solve each of the following systems using elimination. First of all, let me just say that both of these tasks have their place in mathematics learning. However, when considering which task has the potential for the greatest learning, I think we can all agree that that is Task A. Task A is a high-level task, and students aren't told to use a particular procedure. So they can approach this problem using several different methods. They could use guess and check, they can make a table, they can graph the equations to find points of intersection, or they can use algebra. In contrast, Task B is a low-level task. Now let me explain why. Students have to follow a memorized procedure under Task B. Task B is procedural practice only. The mathematics students learn by doing high-level tasks like Task A is very different from the learning that takes place with the low-level task. All right, so our next effective practice is building procedural fluency from conceptual understanding. Conceptual understanding is knowing why the math works. Procedural fluency is knowing how the math works. Fluency means students are able to flexibly choose the appropriate method to solve a problem. They understand and can explain their approaches and why they chose them. And they can produce accurate answers efficiently. When the procedures are connected with the underlying concepts, students have a longer retention of the procedures and can apply them in new situations. So how do we build procedural fluency from conceptual understanding? We build the procedural fluency from conceptual understanding using a sequence of task and learning experiences. We first develop conceptual understanding by building on students' informal knowledge. We provide experiences where students can engage only conceptually based on their prior knowledge. Then we give them opportunities to develop informal strategies to solve problems. This is where they can use their own mathematical understandings and their own strategies. The next activities would help students refine those informal strategies to develop fluency with the standard procedures. And also important is giving them opportunities to compare and contrast different methods to solve the same problem. That builds their fluency, and it also helps them see the connections between the different mathematical representations. And it's also important to allow them to analyze worked examples. That builds their conceptual understanding, those error analysis type problems. We'll explore these strategies further in Chapter 4. All right. So the next effective practice is using and connecting mathematical representations. Students who are able to represent, discuss, and make connections between these different mathematical representations show a deeper understanding of the math and a stronger ability to solve problems. This figure shows the important relationships between pictorial, written symbols, oral descriptions, real-world situations, and manipulative models. Understanding these connections give our students a broader and deeper understanding of mathematical relationships. So students who understand these connections are able to make sense of different mathematical contexts. They're also able to recognize those connections among related mathematical ideas, even new ideas that may not have been formally introduced. And they're able to communicate mathematically using these various representations, and they understand how to interpret them. And this lays a solid foundation for modeling. Now let's check out posing purposeful questions. Purposeful questions work to support meaningful mathematical discourse and generate student thinking. Purposeful questions reveal what our students' current understanding of the math is. And questions probe our students to think and encourages them to explain, elaborate, and clarify what their thoughts are. Questions can help make the mathematics more visible to the whole class for students to think about and talk about. And we can use questions to help our students see the connections among the various mathematical representations. Our questions can prompt students to reflect upon their own understandings and justify their reasonings. And purposeful questions facilitate mathematical discourse. So what kind of questions should we ask? How did you get that? How do you know that? Can you explain your idea? Why? Can you convince us? Did anyone get something else? Can someone tell me or share with me another way? Do you think that means the same thing? Is there another opinion about this? Why did you say that? Purposeful questions and meaningful mathematics discourse go hand in hand. So now let's talk about facilitating meaningful mathematical discourse. Students need opportunities to discuss math. When students are able to formulate their thoughts to share with others, they're deepening their own understanding. Meaningful mathematical discourse provides students opportunities to share their ideas and clarify what they understand about the math. They're able to develop arguments to defend their solutions and either agree or disagree and explain why. Students are able to hear different perspectives from other students, different approaches that maybe they did not think of, and that might cause a light bulb to go off. Through discourse, students' prior knowledge can be linked to the new learning. Mathematical discourse engages students in the learning process, and ultimately, it advances the learning of the entire class. That builds confidence in our students. So as teachers, we have a few tools to help us generate mathematical discourse. One tactic is revoicing what students have said. For example, so you're saying blank. Do I have that right? Asking students to repeat or restate what another student just said is another tactic. Have students explain their reasoning, or if they agree or disagree, and tell why. We can invite students to add on to the conversation. And waiting, giving students the time to respond, and helping them understand that it's okay to take that time so they can think through before they respond is important. And last, turn and talk or think pair shares. That gives students opportunities to talk one-on-one with other students. Each student then has a chance to talk about math, even if they were not part of the whole class discussion. Given these opportunities solidifies what students understand about the math, but it does require teachers to be proactive in facilitating and anticipating what direction the discourse is going to take. And it does require solid classroom management. Our next practice is supporting productive struggle in mathematics learning. Productive struggle is necessary in developing students' conceptual understanding. And we use tasks that promote reasoning and problem solving to support that productive struggle. In productive struggle, students must be required to make sense of a situation and then determine a course of action to take when a solution strategy is not obvious. And once again, the task selected should be doable for students, yet be enough of a challenge so there's something new they must figure out. So let's talk about what productive struggle is. The ultimate goal of productive struggle is to lead students to understanding mathematics. The learning goal should be doable, but challenge students to think and persevere through the task. Productive struggle should yield viable learning results for students. And even though the task is challenging, students should feel empowered and supported in their own learning. Productive struggle should create a sense of hope in our students. The task is challenging, but if I put my mind to it, I can figure it out. In order for productive struggle to succeed, we've got to build a culture in our classroom where students understand that they will struggle and that's okay. They will learn a lot through this experience and develop perseverance to do hard things. But they have to feel supported by us in that struggle. And we have to be careful not to take over the thinking for them, not to tell them how to do it, because they still need to be in charge of figuring it out for themselves. And the last effective practice is eliciting and using evidence of student thinking. This effective practice allows us to gain insight into what our students are thinking. It's critical for us to have that picture of what students actually know and understand, because it allows us to make instructional decisions in real time to respond to our students' understanding. And we can use that insight when developing future lessons. The 8 effective mathematics teaching practices work together to support student learning. This course was just an introduction to each of these effective practices. We will explore each of them further in their corresponding digital course. Well, thank you for taking the time to watch this video presentation. Please be sure to complete your assignments in a timely manner. Start by reading Chapter 1, Setting the Stage. You will have 3 assignments to complete. Assignment 1 is a teaching practices questionnaire. Assignment 2 has 2 parts. The first part is a required reading, so you'll want to print the files out to complete the second part of Assignment 2, which is a questionnaire. Assignment 3 also has 2 parts. Assignment 3 is a discussion forum, so you'll need to post your discussion to the forum and then complete the Assignment 3 forum verification. Thank you so much for taking the Chapter 1 Digital PD. If you should have any questions or issues, please shoot me an email. I hope you join me for another Digital PD.